What's up? My name is Steven. I'm an electrical engineer. I do manufacturing engineering in my job. Today we're going to talk about H-bridges because I've got an H-bridge design that I did that I have in production and is currently being sold to customers. So this video is going to be for the entry level and mid-level engineers. So if you listen to me, you're going to be able to build and design one of these H-bridge circuits. It's going to work. It's going to pass compliance, and you will be seen as a hero, and it will get you one step closer to that promotion. So let us begin. On the screen here is a basic H-bridge motor driver, but it will never pass compliance as is. So they got the very bare bones basics right, but none of the compliance stuff. Because there is no filtering on the motor, you will fail EMI. Because there's no way to shut this thing down in the case of effectively a short, like if the motor stalls, you're going to have a situation where your circuit blows up, where components are blowing, which is not acceptable. So I'm going to go through a design here which will fix these problems. Also, we have another problem, not so much a problem, just as a knowledge gap, which is what is driving these FETs here. It's a diagram, I get it, but as engineers, we need to know this. So we're going to go to a design that I did. It's not the one that went to production because that's proprietary, but this is one that I made, which will help you out. So let's switch over to that. Oh boy! I bet I can imagine what you're saying, switching from that to this. Not even being zoomed in. I bet you're like, WTF. Well, we're going to go in, we're going to explain everything. That way you know why I did what I did. I implemented all the fancy features. You may not need them, and that's okay. Won't hurt my feelings if you take my design and you strip out whatever you don't need. That's called good engineering. So we're going to begin now. So the way we're going to do this is we're going to zoom into the motor and then we're going to work our way outward. The first thing you'll notice is I have filter caps. One from each lead to ground, one from one lead to the other, and then I've got a bidirectional TVS diode going from here. So, if you have a motor, you need to have this filtering. Now, if the motor is far away, it would be nice if you had a separate PCB attached to the motor because distance matters. It needs to be very close to the motor leads. Now, as for these two that are between the leads, sometimes you can get a motor where the leads are on the opposite side of each other. If you're doing motor selection, don't do that. You want the leads close together. Otherwise, you're going to have all this parasitic inductance going on here. So what you can do in that case, if you're stuck with the motor and the leads are far apart, what you can do is just make these traces extra wide. That'll decrease that parasitic inductance. And the reason that matters is because the higher the parasitic inductance, it'll ruin the high frequency filtering of this capacitor. Also note, I put test points here because for some of this other stuff, you may wish to simulate a motor somehow. So we will get to that. Okay, now I just have my PMOS and NMOS, just like the H-bridge, because that's how you do it. So these are actually symmetrical. So I'm just going to go to one side and we're going to dive in. Okay, motor forward, motor reverse. So I have my PMOS right here, but in order to drive this, I have this NMOS here. So I have a pull-up resistor right here. That way, this thing doesn't switch on inadvertently. And then what I do is I use this to turn on. That way it just pulls it down. Another benefit is with my microcontroller, I prefer to use positive logic. That means signal high means it turns something on. Signal low means it turns something off. I don't have to do it this way. I just prefer it because it's more intuitive. So right here is a pull down resistor. And then here is a gate resistor. Now, gate resistors, you can probably get away with not doing them. However, I prefer to have them because what will happen if you don't have it is, since I'm driving it with a microcontroller, your current here, when you first turn it on, will probably go above the absolute max current of your microcontroller pin. Now, it's only for a nanosecond or 2 or 3 or whatever, so it'll probably still work, but I want my product to last forever, preferably. So I prefer to have it. Now, if I was in a super cost-sensitive design, which I'm not, and every penny mattered, or if I had a really, really small board and I was space constrained, yeah, I might get rid of this. Or maybe the product, the warranty is like 1 year and management told me we don't give a shit if it lasts 1 year and 1 day. Yeah, okay, maybe there's some reasons to get rid of that, but I prefer to keep it. Okay, so next, fancy feature time. We've got, here is a soft start. And the way this is done, this is actually a soft stop also. So why the reason why we have this is because it has so many benefits for this motor application. One is that if you turn it on fast, your current's just going to go poof, and then come right down. It's called motor inrush. So we want to smooth out the inrush. It decreases EMI, it's easier on the motor, and it's easier on your power supply. So it's got all the wins. But doing it this way has one big ass disadvantage. That if you do it wrong, you could burn out this PMOS transistor. So what you need to do is look at the safe operating area on the data sheet for this and make sure it'll work. Another pro that I forgot to mention is that this is incredibly easy to simulate. And I can tell you from a design that I did, the simulations almost match perfectly with real world results. So I'm a big fan of this method. Also, you would probably be doing something like this anyways. So at the cost of one capacitor, you've got yourself a soft start. What more could you want? Just make sure that you're in that safe operating area and you're good. And if you do a long enough soft start, you don't need these bolt caps. I have this in a design in production. I tested it. I could barely tell a difference between a very aggressive soft start like this. This is about 80 milliseconds. And between this, having them, not having them, you can barely tell a difference on an oscilloscope. So it's a good idea if you can pull this off. If you can't, then you need these. And that's no big deal, man. It's pretty standard to have these. So another thing I want to mention here is that if you are going to do a PWM, you want to do it on the in channel versus the P channel. Reason for that is because there's going to be switching losses. So P channels are always bigger than in channel just because of how they make it. I'm an engineer, not a scientist. So P channels, they're always going to be physically bigger for the same RDS, and they'll be more expensive. So it's just easier to do it down here. Now, If you're doing PWM, you probably don't need this soft start, because this one is fairly aggressive at around 80 milliseconds. Your PWM, no, these features just don't mishmash together. So feel free to pick and choose what you need, or maybe for your application, you don't need PWM. For my application, all I needed was on, off, forward, and reverse. Now, as I mentioned, the right side matches the left. So the next question we're going to ask ourselves is, how are we driving this thing? Also, we're going to take a look at the safety stuff. In order to do that, we go here. Our input is over here. Now I spec 10.8 to 14.4 volts. The reason for that is because I'm assuming a 12 volt motor, which means that's very easy to be battery powered. In my line of work, it's not unusual for a customer to lug out a lead acid battery with them. It's actually a marine style battery, which can be fully discharged without damaging it too much anyways. So we have to talk about safety. Now, there's two things that could happen. One is that your PMOS and your NMOS, along the same channel, we'll call it, are turned on at the same time. So we got our 12 volt, both are on. That is a direct short. That's bad news. Another problem, which I guarantee will happen. This thing is going to stall one which way or another. That's going to be potentially tens of amps that are going through, and that's just no good for the motor. You risk damaging that, you risk damaging these FETs, and it doesn't work. Nobody wants components to blow. So, by the way, if you don't have that, if you don't account for safety, you will not pass compliance. So you must do that. So we're going to go through a few different ways. One method, if you can promise that this will always be on, this 12 volts is going to be generated from a power supply, well, it already has overcurrent protection, so that might be good enough. Now, in my case, you can either, for the product I ship, you can either have a power supply that does your 12 volts, or it can be powered from a lead acid battery. So in that case, since we're powered from a battery, I don't have this option here. I cannot do that. Another option, which would be not on this board, is a fuse. That's just user accessible. Really not a big problem. Now, by user accessible, let's define that. If you go to a ye olde design, maybe even kind of a new design, depending on what you want your customers to do, you could have it directly on this board. That would mean your customer has to open up the product and then replace the fuse. I don't really like that. I don't want people in my products. Another option is to make it user accessible from the exterior. So just a fuse holder. That's fine. To do that though, you need a label that says what the hell the fuse is and what they should replace it with. I've seen things around the office where this wasn't done, and then it's like, what the hell? And then somebody replaces it with willy-nilly, and then you just have to wonder, is this the right fuse, or did somebody just pick something that'll work? So you need a label. Now, another option, so this is the one right here that I have implemented in a real product. It is a PTC thermistor. That stands for positive temperature coefficient. So as this thing gets hotter, resistance goes up. So if you take that to its logical conclusion, it gets really hot and opens the circuit. That's what we want in a fault condition. Now, there's some downsides to this approach. It takes a relatively long time. So, for your product, that may be good, that may be bad. For this design, it was perfectly fine. So another thing I did before I get to this other safety option, because it's kind of in depth, is that because we have users can do a battery, they may connect it backwards, which reverse polarity protection is necessary in that case. So the reason why I did it here, there's two ways to do it. You can use a Schottky diode, but that's not very efficient. Or you can use a PMOS transistor in this configuration here. Because of my voltages here, I just did a simple voltage divider here. If you Google, you'll see Zener diodes used. That's fine. That's perfectly fine. It's adding one more component, and I like to keep my unique component count to a minimum. But if you need it, you need it. Because your VGS is going to be something like plus minus 20 volts. So for this, not a problem to do it with this way. It's much more efficient here to do it this way, especially at high currents. Now, let's talk about another safety method. But first, I want to go over something that's kind of important for compliance. Now, I did mention that what scenario could these two be conducting? Because somebody was a dumbass when they wrote the software during prototype time. So that's generally how these two would conduct at the same time. Now, you could say, well, just don't be a dumbass and don't program it that way. Absolutely, positively true. For compliance options, or to pass compliance, they don't give a shit. Or at least they shouldn't. Because what will happen is that if your product requires your software for safety features, now that software is deemed as safety critical. Not cool. It sucks. Because that means you can never update your software without going through a compliance nightmare, which will take months, cost thousands of dollars. Nobody wants that. So all safety must be implemented in hardware. Thus, option number 3 is we detect the current going through this motor right here. Because in all the fault conditions, that is very high current. So if these are turned on, that's a short, high current. If this is stalled for whatever reason, very high current, much higher than normal. So we use these shunt resistors here. I did 4 of them, just because that's how the math worked out, where I wouldn't blow it in a fault condition. So notice here, I have 12 volt here, before the shunt resistors, 12 volt motor here after, because we're going to be measuring the voltage. So now what I'm going to do is come all the way down here. So what we have here is a comparator. So we have our 12 volt right here, and then we have the voltage coming off the motor. So through those shunt resistors, there's going to be a voltage drop based upon the current. This is just V equals IR. So R is set. That ain't changing. The only thing changing is our current. So what happens here is that once we get to our high-end current, so I selected 19 amps, the math just worked out well, this will turn on. Then we come to this right here. So this gives me a latch. So what I want is this turns on, and then this InMOS turns on. What that will do is, no matter what these in-channel FETs are doing, this right here pulls this to ground and effectively shuts these off, so no more motor conducting to ground is happening. Awesome. So if I did not have this, what would happen is, oh, we're at 19 amps. This conducts. Oh, we're at 18.9 amps. Well, I guess we can turn off now. And then this would just oscillate between overcurrent and just under the overcurrent. So you would never actually turn the darn thing off. So this right here is a D flip-flop. This turns on and then it latches this to be on at all times. Now, if you ignore this, the way to recover from this is you have to reset the whole device, which is probably acceptable in a fault condition, which plenty of products do that. That's not a problem. So if you, for our previous solution with the PTC thermistor, this will shut off the entire device. This is what we do in the product I sell. It shuts off the entire device. The only downside to that is that it's going to throw people off. It's going to throw the customer off. It's, hey, it turned off. And then because this thing has to cool down before it can turn back on again, it's going to throw people off. But because this trip to safety, this is for safety, man. So it's cool. You can accept a little bit of weirdness in the name of safety. So, next. So I have a microcontroller in this design. So what I wanted to be able to do is say, yo, microcontroller, I turned the safety on. Shit's going down. And then what you might be able to do, if you so desired, is to reset this thing after a certain amount of time. That might be a useful feature if you want self-recovery. It's not mandatory, it depends on your design, but it'd be kind of a cool feature to have, potentially. So, next, I didn't talk about how these were driven. Or I may have briefly mentioned a microcontroller. My place of work, we go for STM microcontrollers. I just picked one that would do the trick. Obviously, this one is 64 pins. You obviously do not need it. I put in a way to program it right here with just a ST link, which is what, if you're doing ST chips, you have one of these. Also of note, I mean, this thing's driven by 3.3 volts, so I got to have a way to get 3.3. And then for the analog input, I didn't know if we were really needed at the time. We do. So I just did a little low-pass filter here to go into our 3.3 volt analog. And then I was like, since we have the analog here, why don't we have these voltages, why don't we just put them into our ADC on here in case we wanted to measure the current? To use for some other purposes. I don't know. Testing? Prototyping? It might be nice to know this. Since I said you can test this with battery life conditions, that might be nice. Then, another thing I did right here was an RS-232 transceiver. And then a connector where it goes in and out with TVS diodes. So the reason I did this is something's got to tell this bad boy here to turn the motor on and to turn it off. So there's more than one way to do this. I mean, I only have 4 pins here, so I just could have done a 4-pin connector and then we do these somewhere else. But I don't want to do it that way. Also, since the way this is done, this will be going to some other board that will then tell this board what to do. Well, there's communication. So I chose RS-232. It may be old, but it still works. What I would recommend against doing is USB. For talking to the outside world, USB works fine. Internally to a device, I've seen it done on another product that my company sells. It was a pain in the ass. And you never know what USB cables are out there. Some are completely non-compliant. Others are fine. But you don't want to deal with that bullshit. Also, we are not done with this design at all. So you'll notice I repeated many of the same components over and over and over again. This is called BOM consolidation, and it's proper. Other design issues where you may question me, which is, why don't you just do a motor driver instead of doing everything discrete? Okay, you are not wrong. But you need to ask yourself, how long is this product going to be on the market? When are we going to update this product? Are we going to update this product? Under what scenarios would we update this product? I can tell you in many companies, the answer is we will only update it if there is a problem. We will never come out with a version 2 unless version 1 is on the verge of not working for some reason. So effectively, this may be out forever. Well, that causes problems if you use motor drivers and if your product is going to be on the market for that long. Because what happens when the motor driver goes into life? You're screwed. Because motor drivers, they're not dropping replacements, man. What are you going to do? Meanwhile, this design has a great strength, which is it's very resilient to supply chain problems. Like these resistors and FETs and capacitors, they'll always be around. No problem. Everything up here, yep, pretty basic. Everything down here, comparator, yep. D flip-flops have been around for decades upon decades. That's cool. RS-232, decades. STM32 chips, not a problem. These guys give like a 10-year guarantee, and it's easy to switch chips. 3.3 volt regulator, not a problem. So this design, while kind of old-timey, while maybe physically large compared to using an actual motor driver, will stand the test of time. And in my line of work, that is a huge, and I mean a huge benefit to doing this. Another thing I didn't mention was kind of current. Not kind of, just the current you're dealing with. So I kind of base this off motor work, which in typical use is about 6 amps. And then I did the 19 amps because if you're at that level, you're definitely in a fault condition. And then there's also one very, very glaring thing missing from this board. And it's not from this board, but it's, how do I test the goddamn thing? If I'm going to get a bunch of these made, I'm going to sell these to customers. How do I guarantee the board is good? Now, I could do functional testing, but I need something to test the board. So as you can, we'll get to see, that's another reason why I did this. Because what I want to do in software is I just want to be able to send a command that literally says motor forward, motor reverse, motor stop, and then it just does that. Or for this, send command motor current, and it returns the current. Or in this case, when we had something with this safety, spit out via serial. safety on, something like that. So it makes it real easy to control this and to troubleshoot, depending on how well you write the firmware. So now let's go into how we're going to test the damn thing. So that's not where I want to go. I want to go here. I'm going to open recent. Tester. Okay. Now we've got our tester. So you'll notice everything on the right here, I just copied and pasted. Pretty much, except the signals. Same microcontroller, same RS-232. Voltage regulator. So what we're going to deal with initially is how to power the darn thing. So what I do over here, the way I do my fixtures, 2 different power supplies. One for the unit that we're going to test. The second is for this test fixture. The reason for this is simple. The board that we're testing could have all the faults in the world. It could potentially trip. If it was any other board that doesn't already have overcurrent protection, it could potentially trip the overcurrent protection on your power supply. And let's say everything was in on this, an overcurrent condition would take out your power supply and then take out the power to your test fixture. One, that's no good. And two, then your fixture has no way of telling you that the board doesn't work. I mean, it's obvious, but you kind of want it to be running, even when your board isn't in a fault condition. That's the way I like it. There's more than one way to do it. So another thing, this is kind of a safety thing, is I always have a relay between our power supply and the unit that we're going to test. Because I'm going to have probably exposed pins, because the board has got to go on something. So, and when we're not doing the actual test, I don't want pins or whatnot energized that shouldn't. Especially if getting it on there is kind of weird, or somebody's just being a dummy and just kind of rubbing the board all over the pins. It happens, man. So I don't want to risk a short. I want the board on. Then we start the test. And then we energize the power. Okay. So that's how we do the power. So another thing we have to do in this case is being able to simulate a motor. So what we can do is, what I've chosen is to simulate 6 amps and 20 amps. 6 amps is our normal condition, 20 amps is our fault condition. So I have a bunch of connectors here. One of them goes to motor terminals A and B. The other, this goes to a 2 1-ohm resistors off the board. These are 50 watts each, so 12 volt, 6 amp, 72 watts. I've chosen that we can get 100. So you can buy some just beefy ass wire round resistors that can handle that wattage. Not a problem. This one was a little bit different because of 20 amps. So the way to do this is quantity 5, 3 ohm resistors, 50 watt in parallel. And this is somewhere in the chassis. This is all off board. Potentially, another way you could do it is put it on the board. They make these heat sinks where you can do that, and you can put a fan on it. But, nah, I don't think we need to do that in this case. Also, we're not going to test for an extremely long duration. A few seconds at best. Designer's choice. So, Fortunately, what we're able to do, because this test is so simple, I've chosen, instead of doing a screen, just do LEDs. Because this follows the KISS principle. It's super, super simple to do. I'm also repeating the same type of circuitry so much. So the way we're doing the test here is, step one, can I communicate with the board at all that we're testing via RS-232? Can I do that at all? If I can, cool, pass. Next thing we do is make the motor go forward. And we're going to do it with the 6 amp load. Under normal conditions, can it go forward? Cool. Can it go backwards? Cool. Now, this one, I don't care what direction does it go, but we're going to do the 20 amp here. Does it fail as it should? Cool. If it does, then everything passed. Done. So it is not enough to just think about, oh, I designed a product. No, at a professional level, you got to think about, at design time, how am I going to test it? And what am I going to test? So you may need to have a whole bunch of test points around. But this method has some big advantages because this is query response. This is basically, yo, do this. And then it says, yeah, I'm doing that. And then this thing can make decisions based upon that. So, and because in the other one, we were looking at current, maybe we could profile what we should be seeing. We can make decisions off that. I didn't put that in here, but maybe you could. So my favorite is query and response type of testing. And otherwise, if you don't do that, you got to have a whole bunch of test points, or you got to find maybe a connector that has what you need and go through there. And a bunch of weird stuff could potentially happen if you don't design initially for testing in mind. So, I think we got everything done here. Let's go back. My bad. My bad. We'll get it. This, in general, is how you do an H-bridge design with a DC motor. So I hope you got something out of this. I hope I brought up some topics for you to think about. Because if you can think about all this at design time, that's less problems for you. If you can get a pretty much mostly working thing at the prototype stage, you're doing well. Because at the end of the day, we want our designs to work. We want them to be safe. We want you looking like the hero. Because we want you to be getting the good projects, not being pigeonholed in some bitch work. We want you getting the good projects. We want you getting the promotions. We want you getting them monies. So I'm going to leave you off here. So, and everybody, y'all have a great day. Bye.